Now that we have derived the equations for Kalman filter, namely the forecast equation, the forecast mean, the forecast covariance, observation, the analysis step, the analysis mean and the analysis covariance. In this case the system is linear, the noise is Gaussian, therefore the forecast is a Gaussian random variable, the observations have Gaussian distribution, analysis have a Gaussian distribution, as we had observed several times in the previous lectures, that Gaussian distribution is the only one that is decided uniquely by the mean and the covariance. So if I compute the analysis covariance and the analysis mean, I essentially characterize the entire probability distribution. Against this, now I am going to describe a couple of simple examples to illustrate the dynamics. First I am going to talk about scalar dynamics with no observation. That means this is called stochastic dynamics. So let A be a scalar positive, Wk be a scalar Gaussian random variable with mean 0 and variance q, q is the variance, and x naught is m naught p naught. So p naught in this case is a scalar, p naught is a scalar. The dynamics is given by a simple scalar linear dynamics, xk is equal to a times xk minus 1 plus wk. So we have talked about the value of a, wk, x naught. The solution for this linear occurrence can be given by this. I would like you to verify the correctness of this equation by substituting back into the by using the method of substitution. That's the best way to describe it. So from here we get this solution. Now I can take the mean of both sides. Please remember the mean of Wj is 0 and Wj's are temporally uncorrelated. Therefore if I took the mean, the second term does not contribute anything. The mean of the state at time k is a to the power of k m naught. The variance of the state xk at time k is pk, that is equal to variance of x a times xk minus 1 plus wk. If you multiply a random variable by a constant, you multiply the covariance by the square of the constant. Variance of the sum is the sum of the variances, since the two quantities are not correlated. Therefore the variance of the state at time k is given by this, and this xk is essentially the forecast because I am simply using the model. So a to the power of k mk is the mean of the model forecast. The a square pk minus 1 plus q is the variance associated with the model forecast. Please understand this variance has two components, one coming from the initial covariance, the distribution of the initial condition, second coming from the model noise. This is the scalar analog of the vector forecast covariance we have already derived within the Kalman framework. And if you now substitute pk minus 1 in terms of pk minus 2, pk minus 2 in terms of pk minus 3 and so on, and open it up and simplify, pk depends on p naught a to the power of 2k p naught plus q times a to the power of 2k minus 1 divided by a square minus 1. Again I would like you to verify by solving this simple linear recurrence relation. So for a given m naught, p naught and q, what is m naught? The mean of the initial condition, p naught is the covariance of the initial condition, q is the variance of the observation, is the variance of the model noise. I would like to be able to now analyze the behavior of all the moments. What are the moments? The first moment and the second moment of the forecast. That simply depends on A now. That simply depends on A because all the other factors are fixed. For a given M naught, P naught and Q, the behavior of the forecast moments, the first moment and second moment, depend only on A. When A is less than or equal in the region A greater than 0 less than or equal to 1, the model is stable. What do you mean by the model is stable? The model solution without the the model solution doesn't explode to infinity. In fact, it can be shown from the solution of the model equation in the previous step. Xk is equal to a to the power of x naught plus that. We can readily verify that limit xk as k constants is 0 when pk when the limit of pk is also given by that. So the limit of xk is given by this, the limit of pk is given by this, and I would like to be able to tell you that this essentially comes from the first equation, which I would like to call it star, which I would like to call it star. So if this is star, if this is double star, in the next equation both of this comes from star and double star. Now if A is less than if A is finite but greater than 1, the model is unstable. That is the complementary part. The model is unstable. The limit of xk goes to infinity, the limit of pk also goes to infinity. When A is equal to 1, the model defines a random walk. So in this case xk plus 1 is equal to xk plus wk plus 1. So it executes a random walk on the real line. In this case xk is equal to x naught plus wk. Wk is the sum of all the noises. So E of xk is m naught. Pk, the variance of xk pk is equal to p naught plus kq. Now you can see even when A is equal to 1, while the mean remains the same, its covariance increases linearly as p naught plus k times q. So this is simply the analysis of the behavior of the solution of the stochastic linear dynamics given by xk plus 1 is equal to a times xk plus wk plus 1. Now I would like to bring in the data into the picture, and that brings, I continue the same example. I am now going to talk about Kalman filtering. So without data I simply make predictions with model alone. We talked about forecast mean, forecast covariance. We analyzed how the forecast covariance varies for different regimes when A is A is positive in between 0 and 1, when A is positive and greater than 1, when A is equal to 1. So we divided the range of values of the parameters into 3 subregions, one stable, another unstable, another corresponds to the random walk. In 2 of the 3 cases, when A greater than 1 or A is equal to 1, we see that the variance go to infinity. The random walk model is very interesting, and we may have occasion to talk about it later. Xk, so now let us continue. Xk plus 1 is equal to x wk plus 1. Wk plus 1 is again the noise with 0 mean and variance q. Zk is equal to h times xk plus vk. H is a scalar, vk is a scalar. Vk is 0 mean, is a Gaussian random variable with a 0 mean and variance little r. Now I have to distinguish between forecast and the analysis. Therefore forecast state is equal to a times the analysis at time k. In other words, I am going from time k to time k plus 1. This transition is what we are talking about. Earlier we talked about the transition from k minus 1 to k. Absolutely there is no difference except for the values of the indices. So pk plus 1 f is the forecast covariance at time k plus 1. is equal to A square times the analysis covariance at time k plus q. The analysis itself is given by the forecast plus Kalman gain times zk minus hkf. The Kalman gain is given by this formula, which can be simplified as pk hat h r inverse, and then the analysis covariance is given by this expression pkf minus something. I am trying to subtract a positive quantity from pkf, therefore the analysis covariance becomes less. So pkf r, so analysis covariance is equal to forecast covariance times r divided by h square times pkf plus r inverse. So this is the very simple expression for the analysis covariance as a function of k. All these things arise from the derivation of the Kalman filter, except that we have substituted the corresponding formula. So now, given I have the equations for the analysis covariance, forecast covariance, I can now talk about the stability of the analysis part. In order to understand the stability of the analysis part, in other words, what do I want to find? Does the analysis go to infinity as time goes to infinity? Does the analysis comes down to 0? What happens to the analysis error? What happens to the forecast error as a function of the model parameter? These are some of the things that we would like to be able to understand to analyze the stability of the filter. So in this case, forecast is given by the forecast at time k plus 1 is equal to a times 1 minus kh kkh xkf plus a times kkzf zk. The analysis at time k is given by this. I would like you to go back to what we are doing. Look at this now. I can substitute in this equation. How do I get this? I can substitute the analysis expression into the forecast expression. That's exact. I can also substitute the forecast expression into the analysis expression, so that analysis at time k plus 1 can be expressed in terms of forecast at time k. I'm sorry, analysis at time k. That means I can get a recurrence in the analysis value at time k and k plus 1. I can also get the forecast expressions connecting the forecast at time k plus 1 to forecast at time k. That is the important part of the recurrence. In here, analysis depends on forecast depends on analysis. By mutually substituting each other, I can express forecast depend on forecast, analysis depend on analysis at time k plus 1 to time k. That is the recurrence we are talking about. So by substituting this, I get one recurrence for the forecast, the one recurrence for the analysis. So if I have a forecast, I can compute the forecast error. If I have analysis, I can compute the analysis error. We have already seen the forecast is equal to forecast minus the state given by the model. Analysis again, analysis error can again be computed, as we have already seen how to handle the analysis error forecast errors. I also have the expression for the forecast covariance in terms of analysis covariance, and in this case covariance is essentially a variance. The forecast variance is a square times the analysis variance plus q. Here again the analysis variance depends on the forecast variance. Again I can substitute each other. I can substitute this in here, I can substitute this in here. I can then relate forecast at time k plus 1 to forecast at time k, analysis time k plus 1 to analysis at time k. If you do that, the example continues. Now after that substitution, I get this equation. Yes, you can see this is heavily there is a lot of heavy algebra. Now divide both sides by r. If I divide both sides by r, I get this relation. So what does it tell you? This tells you the forecast covariance at time k plus 1 is related to the forecast covariance at time k. Now look at the expression on the right hand side. The forecast covariance occurs both in the numerator and the denominator. So this is the nonlinear recurrence relation. This is a nonlinear recurrence relation. Therefore, I am now going to change the notation. I am going to define Pk is equal to Pkf by R. If I did this one in view of this one, you get this relation where alpha is the ratio of Q over R. This is an interesting ratio. What is Q? Q is the variance of the model noise, R is the variance of the observation noise. So the ratio of the two noises is alpha. So if you look at this normalized forecast covariance, see that is what I want to emphasize in. This is the dynamics of evolution of the normalized forecast variance. What is the normalization? I have normalized this with respect to the variance of the observation. I have normalized this with the variance of the observation. So if you look at this relation, you can see A is a constant, Pk plus 1 depends on Pk, H is again a constant, alpha is the ratio. So this expression on the right hand side depends only on A, H and alpha. This type of recurrence relation in mathematics in the theory of difference equations has come to be called Riccati equation. It is a first order equation. Why this is the first order equation? K plus 1 depends on K. It is scalar because we are concerned with only with the variances. It is nonlinear obviously because the right hand side depends on Pk in both the numerator as well as the denominator. Therefore, it is a first order nonlinear scalar recurrence. The particular structure has been around for a long time. It is due to Riccati, an Italian mathematician. There is a Riccati equation both in ordinary differential equation as well as in difference equation. Here we are concerned with the difference equation analog of the Riccati equation. This equation is not easy to solve because it is nonlinear. So now I am going to talk about the asymptotic properties of the forecast covariance. So let us see how we got here. Once more, I substituted the quantities because forecast depends on analysis, analysis depends on forecast. I mutually substituted them and made forecast dependent on forecast, analysis dependent on analysis. Likewise we did for the covariances as well. Once we did the covariances, I am now trying to single out the forecast covariance. I normalized the forecast covariance by the observational covariance R and rewrote the equation that resulted in a normalized forecast covariance dynamics, which is a difference equation. It is a first order scalar nonlinear difference equation. Now I am going to look at the asymptotic properties of this first order nonlinear scalar equation. Why? What is the aim? The aim is the following. I would like to be able to understand the regimes excuse me, namely under what condition does the covariance grow, under what condition the forecast covariance die down. That relates to analysis of stability of the forecast covariance. Now once I analyze the stability of the forecast covariance, the corresponding properties of the analysis covariance follow immediately because forecast covariance depends on analysis covariance depends on forecast covariance. So behavior of one, asymptotic behavior of one will imply the asymptotic behavior of the other. So to that end, I am now going to assume H is 1 without loss of generality. What is H? H is just a parameter that relates to converting the state into the observation. So please remember Zk is equal to H of xk plus Vk. In this case I am assuming H is equal to 1. I am assuming H is equal to 1. So in that case my equation now becomes simpler like this: a square Pk divided by Pk plus 1 plus alpha. I would like to be able to understand the behavior, the long term behavior of this equation, this important equation star here. In order to understand the long term behavior of this, what do? I am trying to look at the increment Pk plus 1 minus Pk. That means how much pk plus 1 differs from pk at the kth step. If I substituted pk plus 1 in terms of pk and did the algebra, I get this relation. Which can be now written as a ratio of a polynomial divided by pk plus 1. The polynomial in pk is given by the expression on the numerator, which we can readily identify. Yes, if you are trying to read through, there is a ton of algebra, and I think the only way to be able to do it is to be able to hit all the major developments, and that is what I am trying to do, leaving behind the details of the derivation of the algebra to the reader. So when does this recurrence relation on pk converges? That means pk plus 1 is equal to pk is the condition for convergence. Pk plus 1 is equal to pk is the condition for convergence, at which time delta k is 0. At which time delta k is 0, delta k is the equilibrium. If delta k is 0, then g of pk must be 0. So now you can see how we have changed the variable from pk to delta k, expressed delta k as a ratio of two polynomials in the normalized forecast covariance pk. We have already now identified delta k being 0 is an equilibrium point, at which case pk plus 1 is equal to pk. That means pk does not change, it has come to a stable value. Because delta k is the ratio of two polynomials in pk, the numerator polynomial must be 0 for delta k to 0, and that is where we are. So this calls for analyzing the behavior of the solution of the numerator polynomial. The numerator polynomial is equated to 0. It is rewritten, it can be rewritten by changing the variables. So I am going to concoct a new variable beta. Beta is equal to a square plus alpha minus 1. Please understand, a is the model parameter, alpha is the ratio of the two variances, model noise to observation noise. So I can concoct a new symbol beta to this term. So if I did that, my polynomial becomes this. This is a second order polynomial in pk. I can now apply the standard rule for finding the roots of the second order polynomial. There are two roots, p superstar and p substar. These expressions are now dependent on only beta and alpha. Please recall, beta depends on a and alpha. So I have a numerator polynomial g of alpha, which is a quadratic. I have solved it. So I now know the value of the equilibrium, at which point the forecast covariance will settle down. There are two equilibria, p superstar and p substar. Now we would like to be able to understand the behavior of the solution around these two equilibria to see whether the slope of it is increasing or decreasing, such as it is like this or it is like this. This corresponds to unstable, this corresponds to stable. Why this corresponds to stable? If I am here, this is pk, pk plus 1 is smaller. If I am here, this is pk. So from here it pushes here, from here it pushes here. However, if I am here, in this case, if I am here, it grows bigger. If I am here, it grows bigger. So it goes away and it goes away. Therefore this is unstable, that is stable. Stable means if I am to the left of it, it pushes to the right. If I am to the right of it, it pushes to the left. That means the stable equilibrium is an attractor in the neighborhood. An unstable equilibrium is a repeller. If I am to the right, I move to the right. If I am to the left, I move to the left. So this is the repel. Here attract, attractor. So to be able to see something is a repeller and attractor, we have to get the slope of g of alpha. G of pk at the point where the equilibrium occurs. where the equilibrium occurs. Therefore, the general expression for the gradient of g prime of pk is minus 2 pk plus beta. Now we are going to evaluate by setting pk is equal to p superstar. Superstar is the star is a superscript. In this case, the derivative is negative. So please understand, here the derivative is negative, here the derivative is positive. So the derivative negative corresponds to an attractor, the derivative positive corresponds to a repeller. So you can readily identify this is p star, this is p sub star. So p sub star is unstable, p star is stable. So we need to consider only, again I want to re-emphasize, one is an attractor, another is a repeller, stable unstable. Therefore, in the limit pk will go into the attractor. When pk goes into the attractor, at the attractor p star is equal to a square p star divided by 1 plus p star plus alpha. So you can readily see this must be the expression for the normalized forecast covariance at the equilibrium. At the equilibrium you can solve this equation for p star and you can get the exact value. I would like to now give strongly recommend that you plot g of pk versus pk. You know g of pk is a very simple expression, and I also would like you to plot delta k versus pk and verify all the claims that we have taught thus far. I think these are very important exercises to understand thoroughly the long term behavior of the forecast covariance when the model is scalar. Now you can see the p star and p superstar and p substar depend on beta and alpha. Beta depends on a. So you can find the regions in the parameter space that gives rise to stable behavior, that gives rise to unstable behavior. I hope that's very clear. So what does this tell you? Again, I want to re-emphasize this. This too essentially tells you that no matter where you start, pk plus 1 will come and settle at this point depending on the values of a, alpha and so on. So using MATLAB, I would like you to be able to verify all these conclusions, and that's an important part. That's an important part of the analysis. That's an important part of the understanding of the Kalman filter dynamics. Once I know it converges, I think it makes sense to ask ourselves the question, how fast does it converge? That relates to rate of convergence. This is not the first time we are talking about rate of convergence. We have talked about rate of convergence when we talked about gradient methods and especially when iterative methods like gradient method. So in any iterative algorithm there are two questions one should ask: does it converge? If it does, at what rate? So we are going to quickly indulge in the calculation for the rate of convergence. Let yk be equal to pk minus p star. So what is pk minus p star? Pk is the current value of the normalized forecast covariance. P star is the asymptotic value at the stable equilibrium. So I would like to be able to measure the difference between where I am and where I will hit sooner or later. So I also know the equation for pk plus 1. So we would like to be able to compute the rate at which we converge. So yk plus 1 is equal to pk plus 1 minus p star. So I am going to substitute pk plus 1 p star, simplify, use the relation yk, this must be pk, sorry, p sub k, pk minus p star is yk. This is also pk, sorry, this is also pk, p sub k, p sub k. So if you, this is also p sub k. So if you can now see, we have already gotten an expression for yk plus 1 relating to yk. And what is yk? Yk is essentially the difference between pk and p star. So if I consider 1 over yk plus 1, that is given by this expression. So this expression is essentially coming from here, which I can rewrite like this. Again, this is yk, sorry, y sub k. Now I can rewrite this expression as a sum of these two terms. Again, a little algebra will give you. So 1 over yk plus 1 is equal to 1 over yk times a constant plus another constant. So I am getting a recurrence for 1 over yk plus 1. So please go through the algebra now. Yk is the distance between pk and p star. I am trying to express yk plus 1, which is the distance between pk plus 1 and p star, in terms of yk. So I am trying to get a recurrence in yk. Instead of trying to get a recurrence in yk, I can equivalently get a recurrence in 1 over yk. Why? We would like to be able to consider a quantity which is easy to analyze. That is all what the matter here is. Now I am going to change the variable once more. You can see how many different ways in which we can look at it. So 1 over yk is zk. That essentially tells you the previous equation at the bottom of slide 30 now becomes a linear equation. The linear equation is given by zk plus 1 is equal to c times zk plus b, where c is a constant and b is a constant. Hey, that is the key. So let us go over this quickly once more. I have a Riccati equation. I am going to change the variable for the Riccati equation. I have a Riccati equation for pk. Now I have a Riccati equation, I have a corresponding nonlinear equation for yk plus 1. While I have defined yk, I am trying to rewrite it as a recurrence in 1 over yk. It turns out the Riccati equation, after making these transformation, these two transformation, namely yk is equal to pk plus 1 minus p star, 1 over yk is equal to zk, the Riccati equation becomes linear. Linear equation can be very easily solved. I can iterate the linear equation. So this is the solution for the linear equation, which can be written like this. So zk is given by this expression. That is an important expression. So 1 over zk is yk is equal to 1 over zk defined by this. So let us not worry about this part. In this equation, b divided by c minus 1 is a constant. So when c is greater than 0 and c is when c is greater than 1, when c is greater than 1, ck to the power c to the power k goes to infinity. Therefore yk will tend to 0, yk tend to 0. So you can readily see that this expression is equal to c to the power minus k times a constant. Therefore when c is greater than 1, this yk tends to 0 at the exponential rate. I think that is the importance of this. So c is equal to 1 plus p star by a whole square, and that must be greater than 1. So under the condition that c is greater than 1, which in turn relates to 1 plus p star divided by 2 square is greater than 1, we can really see yk converges at an exponential rate. So this is an exponential convergence. That's an important conclusion. So what is that we have accomplished? We have accomplished the following. By converting a sequence, by converting the Riccati equation to a sequence through a sequence of transformation, we converted it a nonlinear equation to a linear equation, which we then solved and found conditions under which this linear equation, solution to which go to go to infinity, which in turn means zk goes to infinity. Zk goes to infinity when c is greater than 1. When zk goes to infinity when c greater than 1, yk tends to 0. Now please realize the definition of yk. The definition of yk is pk minus p star. Yk refers to the distance between the current value of the forecast covariance with the asymptotic value. So that distance goes to 0 at an exponential rate, and this gives you values of the parameters under which the Kalman filter forecast covariance not only converges but also converges at an exponential rate. Excuse me. The rate of convergence continues. Once we have, again we have assumed h is equal to 1. Once we have the convergence of pk, we can now conclude the convergence of pk hat, which is the analysis covariance. The expression for pk hat divided by r is given by this equation. If I took the limit of this, pk hat tends to a particular limit because pkf tends to a particular limit, and this is the limit of the analysis covariance. So analysis covariance converges with forecast covariance. They work in locked step. Now I am going to go back to the analysis of what is called stability of the filter. Stability of the filter. H is 1. This is the forecast covariance. Sorry, this is the forecast covariance. I'm sorry, did I say forecast covariance? That's wrong. This is the forecast error. The forecast error can be simplified to be this. The forecast error recurrence has two parts, the homogeneous part and the forcing part. The homogeneous part is given as the following. The forcing part consists of two error terms, ak, kk, vk plus wk plus 1. So this is the stochastic part, this is the deterministic part. The deterministic part is also the homogeneous part because this is the forcing. Please recall kk, the Kalman gain is given by this. So from here I am going to get 1 minus kk as this. So the Kalman gain kk is given by this formula, which is pk divided by pk plus 1. From that you can readily infer 1 minus kk is equal to 1 over pk plus 1. Substituting these and simplifying, it can be verified that the E bar f of k plus 1 is given by this recurrence. Substituting the value of p star, it can be verified that E bar f k plus 1 is equal to 1 over square root of c times E bar f k. Since c is greater than 1, 1 over square root of c is less than 1. That means in going from time k to time k plus 1, the error reduces. Therefore, if you compute the error ek bar f with respect to the state at time capital N, ek bar f is given by 1 over square root of c to the power k minus n times E bar f by n. So n can be thought of as a starting time. Since 1 over square root of n 1 over square root of c is less than 1, as k goes to infinity, the term 1 over square root of c to the power k minus n tends to 0. Therefore, the overall error goes to 0. This in turn means the filter is stable. So we have analyzed all the properties of the Kalman filter and have illustrated the derivation as well as the nuances with respect to several properties of the Kalman filter equation using a simple static linear dynamics. Thank you.